Hi, let's talk confidence intervals using the Z-critical score. So, let us look deeply into confidence levels, and a new term is going to come up, significance level. Let's compare them. So, if I'm 90% confident that something will happen, my significance level is 10%. And we know that a whole is out of 100%, and if we're 90% sure, it means that we're 10% not sure, right? One is called the confidence level, one is called the significance level. One is represented by alpha, that's that symbol next to confidence level, and in order to get the significance level is 1 minus alpha. So we can have different confidence levels. A 99% confidence level would mean a 1% significance level. An 80% confidence level would mean a 20% significance level, and a 95% confidence level would mean a 5% significance level. Now, we're going to learn how to calculate the confidence interval when the standard deviation is known. So the assumption is the standard deviation of the population is known. In order to calculate the confidence interval for the mean when the standard deviation is known, we compute what is called the upper control limit and the lower control limit. Similar to how when I gave that person $100, I went back on my word and I said I may give you between 80 and 150. $80 was my lower control limit and 150 was my upper control limit. Here are the formulas for calculating both. Let's look at the upper control limit formula. We're taking our sample mean, and then we're adding our Z critical score times the standard error of the mean. Hold up. I think we're familiar with the mean, and we should be familiar with the standard error of the mean, but I'll give you that formula. But what is definitely new here is Z critical, and we're going to talk a little bit about that. In order to compute the lower control limit, the formula is similar except that we're subtracting for the lower control limit. Now, as I mentioned before, let's talk Z critical. It's very important that we go back to this curve and we're saying, oh, yes, that's the curve again. It is the bell-shaped curve. Things are symmetrical, meaning that if we cut it in two, both sides are the same. It follows the normal probability assumptions, right? The normal distributions. Okay. Now, this is an example that we have a 90% confidence level. We're 90% sure of something. We know that majority of our points fall within the middle of this curve. And so 90% is represented by the orange area, and as a decimal, that's 0.90. We do know that the area under the curve also equals 1. And if the area under the curve is 1 and 0.9 is represented by the orange portion, and this is normal distributed, so points are going to be to the left and to the right, we have a difference there of 0.1, right? That 10% difference in order for our area under the curve to add up to 1. We do know, though, that it's symmetrical. So on one side, we're missing 0.05, that's 5%. And the right side, we're missing 0.05. Again, that's another 5% would add up to the 1, the area under the curve. Now, it's very important that when we are doing our problems, we understand if we need information to the left of the curve or we need information to the right of the curve. And most times we need information to the left of the curve. And to the left of the curve, the area under the curve is 0.9, which is represented in orange, and 0.05 more, which is further to the left of the orange. And so I point that out because I want to say to you that when we go to the tables to get our answers, we are going to be looking for probabilities of 0.95 if our answer is going to be to the left of the curve. And that is because the area to the left of the curve is that 0.9 plus one of the 0.05s, and that takes me to 0.95. Now, if we wanted information to the right of the curve, that's different. That would be 0.5. Now, what do I do with the 0.95? We must use the cumulative probability for the standard normal distribution table. And in the text that I have, it is table 4. In your text, it might be a little bit different if you're using a different text. But here we have the cumulative probabilities. And remember, we're looking for 0.95. And when we're looking for probabilities, we're really looking in the middle of the table because that's where the probabilities lie. And we need to read off the z-score. So I've circled where I think 0.95 lies. It lies between 0.9495 and 0.9505. And if you do a little bit more calculation, you realize that it lies in the middle. So I'm going to go to my left where I circle my number and I'm going to match all the way over to my z. And the first digits of my z is 1.6. And so if I come back over and I match up to the top, I see that it's going to fall between 1.64 and 1.65. And so halfway is where it is. So my z-score is 1.645. My z-critical for 0.05 is 1.645. So here's a table that provides a snapshot of what each confidence level would yield as a significance level. And then when you go to the table and match its z-critical score, this is what it would be. This is a good cheat sheet to use for further calculations, hoping that the confidence level will be either of the 5. But let us look at 80%. At 80%, our confidence level would give us a significance level of 20% because it's 1 minus alpha. And then if we imagine our bell-shaped curve and we have our 0.8 in the middle and we're missing 0.2, it's symmetric, so we're missing 0.1 to the left and 0.1 to the right. If we want to find the area to the left, under the left of the curve, it's 0.8 plus 1 of the 0.1. So we're looking for a z-score that matches a probability of 0.9, which is 0.8 plus 1 of the 0.1s. And when we go to our table, we would match it up again and we would look for the probability in the middle, and our 0.9 will yield us a z-score of 1.28. So the confidence levels, 95%, 98%, 99%, has these z-critical scores. Now, there are 3 steps used to calculate the confidence interval for your problems. And step 1, you are calculating the standard error of the mean, which means you're taking your standard deviation, dividing it by the square root of n. Step 2, you have to find your z-critical. And then step 3, you're going to use your upper control limit and your lower control limit formula to find your confidence levels. Here's what an example looks like. A local salon wants to estimate the mean visiting time for customers on a Saturday, the busiest day of the week. This information may help the owner plan for the number of customers which may be able to book appointments. Now, assume that a sample of 30 customers gives a sample mean of 42 minutes and the population standard deviation is 2.1. Calculate a 90% confidence level for the population mean. So we don't want to say that the population mean is going to be the sample mean. We want to say that it's going to fall between 2 points. Now here's the calculation. If you notice, my calculation is handwritten, and that's because I want you to take some notes. I don't want you to take your phones out and take a snapshot of what I did. I want you to actually write it and calculate it. There's power in writing, calculating, and it leads to comprehension. So what I did, I wrote out the things that I knew from the problem. I knew that the standard deviation was 2.1. I knew that the number of persons in the sample was 30, and I knew that the mean time for the customers is 42 minutes. Step 1. I'm calculating the standard error of the mean. I take my standard deviation and I divide it by the square root of n, which is the square root of 30. That gives me 0.383. Step 2. I find my z-critical score for 90%. And my z-critical score for 90% means that I'm missing 10% and it's 0.05 on each side, so I need to find z-critical for 0.05. However, I know that when I look under the curve, I'm looking for 0.9 plus 1 of the 0.5 because I'm looking for the area to the left, and I'm looking for 0.95 in the middle of the cumulative probability table, and that gave me 1.645. You could do that, or you could use the cheat sheet table that I gave you before. Step 3, it's easier. I'm just calculating my upper and lower limit. I'm taking my mean, and then I'm going to add my z critical times my standard error of the mean. And for my lower control limit, I'm doing the same, but I'm subtracting. So let's do the upper control limit. 42 plus 1.645 times 0.383. But remember the rules of BOMDES or POMDES, depending on your territory, you may refer to it differently. We multiply first. So we have to multiply our 1.645 by 0.383, and then we add 42 to that to get 42.63 minutes. We do the same thing for the lower control limit, and we subtract to get 41.37 minutes. But what does this mean? Well, if you ask me, it means that we are 90% confident that the population mean number of visits each Saturday is between 41.37 and 42.63 minutes. I must thank you for watching and sticking throughout this problem so far. I must point out to you, though, this concept of margin of error. Now, the margin of error means that there's a section in your upper control limit and your lower control limit formula to the right that says z critical times the standard error of the mean. That is what is called your margin of error. So if you know your margin of error and you know your mean, you can basically calculate your limits, right? With the margin of error, the upper limit, the mean is going up by that figure, and the lower control limit is going down by that figure. Now, this can be calculated using the Excel function, not the upper control limit and the lower control limit I'm referring to, just the margin of error. If you use the confidence.norm formula, you will get the margin of error, but you do have to go back to your formulas to calculate the upper control limit and the lower control limit. I would like to leave you with a few tips. 1, ask the question, what do I know? I knew the standard deviation, I knew my n, and I knew my mean. And 2, follow the 3 simple steps that are outlined. Thank you for viewing. Bye.